Okay, so we're going to keep looking at related rates today, but this time we're going to talk about the infamous ladder problems. These are like a favorite on entrance tests and all sorts of things. So, we're going to talk about ladders and like a ladder when it's next to a tree, right? And the ladder falls and kaboom, you fall. So that's where we're going. These problems are all very similar. So you'll start to see the pattern. Okay, so let's go ahead and look at one of these. So these are all going to really follow the same general pattern with not a whole lot that changes. And we're going to use a different theory than we used with circles. This time we're going to use implicit differentiation. And I think you'll see that it's really useful here, but it's just one more tool to have in your toolbox and just a different way of doing things. Okay, so we have a 12-foot ladder is leaning against a tree. Okay, so here is my tree. Okay, here's my tree, and there's some, apples in the tree or cherries, whatever. Okay, and it's a 12-foot ladder leaning against this tree. So my ladder is leaning against the tree. My ladder is 12 feet. Okay. Oh no, the top of the ladder is sliding down the wall. Okay, so we're sliding down the wall, or wall. Oh dear, walls, trees, whatever. Okay, at a rate of 2 inches per second. So immediately we need to deal with this because now we're dealing with inches. So 2 inches is how much of a foot? Well, if it has 12 inches, this is 0.16 inches or feet per second. So this is falling at 0.16 feet per second, right? Okay. How fast, so question mark, how fast is the bottom of the ladder moving away? So the bottom of the ladder is also moving away, right? As the ladder falls, the bottom's moving away until it's flat. So our question is, how fast is this moving when the top of the ladder is 8 feet from the ground? Okay, so the rates are continuously changing, right? So the rate at which this is falling is going to impact the rate, the rate at which this side moves is going to impact the rate at which that moves. So we want to know exactly what's happening as in a snapshot at 8 feet. Okay, so there is a triangle here. I assume everybody can see the triangle that is made, right in here, right? This is a triangle, a right triangle, assuming this is a nice straight tree. Okay, so we need a formula to start with. And what's the only formula any of us have for right triangles? Well, it's Pythagorean theorem, right? A squared plus b squared equals c squared. So let's rewrite this. This is definitely our height over here, and this is our length, and this is our hypotenuse. That's our ladder, but it's a constant, and it's not changing. The ladder itself doesn't have a rate. That you can't make your 12-foot ladder smaller. Okay, so what we really have is h squared plus L squared equals 12 squared, because 12 is my hypotenuse. And we need a derivative. So we're talking about rates. And remember we said that rates equal d dt, right? Because it's the derivative with respect to time. So we're dealing with height and length, and we want to know about the height, the rate of the height changing. So it's the dh dt, right? So we need the derivative of h with respect to time, and we need the derivative of length with respect to time. So what we're going to do is we're going to take this whole thing, and we're going to use implicit to take the derivative with respect to time. Okay? So we're going to take the derivative of h squared with respect to time. And that is going to be, what's the derivative of h squared? Well, it's 2h dh dt, because we want the derivative of height with respect to time, plus the derivative of length squared, which is 2L, times the derivative with respect to time. So that's going to be dl dt. And that equals 12 squared, which is 144. And the derivative of 144 is 0. And we don't need that rate because it doesn't exist. So if you look at this now, we've got this formula that's really exactly what we were going for here. So here we've used implicit to take the derivative with respect to time. So we have 2h dh dt, 2l dh dt equals 0. And we have 4 variables here, right? We have an h, oops, hold on, let me highlight that. We have an h, we have a dh dt, we have an l, and we have a dl dt. There's 4 variables that need to be filled in, and if we come over here, we have some of that. Like this, oops, nope, that's not the color I wanted. This 0.16 is a rate, and it's the rate of height. Well, that means that is dh dt, isn't it? Why can't I get this right? dh dt. That's dh dt. In the height that we were talking about, our h, we were told that we want to know what's happening when the height's 8 feet. Now, dl dt is what we're looking for, right? And then there's this matter of length. So if we take a snapshot, we can figure out that we've got a triangle here that's 12 and 8. Can't I figure out this bottom length really quick using Pythagorean theorem? Can I say 8 squared plus x squared equals 12 squared? And if I do that, then I get, let's say, the square root of 144 minus 64 is 8.9. So this is 8.9. So my length at that very moment is 8.9. So I can come plug all this in. So I can say 2 times my height, which is 8, times the derivative, the dh dt is 0.16, plus 2 times my length, I just figured out in that moment, is 8.9. dl dt is what I'm looking for, equals 0. So now I can take that and I can solve that, right? Like I'm going to say 2 times 8 times 0.16 equals 2.56 plus 8.9 times 2 is 17.8. dl dt equals 0. And then I can just rearrange and solve for dl dt. And if I do that, I get negative 0.18, and I was dealing with feet per second. So you can see that, and that means it's decreasing, I guess, right? That's what that negative is going to be. So that means that the rate at which this is changing is not equal to the rate at which the height is changing. So therefore, that's why we have to do this. So let me go through this one more time. We used implicit differentiation to take the derivative of the formula we had. So that meant when we took the derivative of height, we multiplied by dh dt. That's the implicit piece. Then we took the derivative of the length and multiplied it by dl dt. The derivative of a constant is 0. We plugged in what we knew. We knew our height at that moment. We knew our rate at that moment. We were able to find our length at that moment, and then we could solve for the rate of change of length at that moment. Another key to this was making sure we kept our units the same, like we didn't deal with inches and feet. We had to convert our inches. Okay, let's try another one. All right, oops, wow, okay. So let's try another one. Now this one's gonna be almost the same, but not quite. First of all, we're going to switch units because that's fun. And then we're going to look at what's changing this time. So this one is a little bit different. A 4-meter ladder is resting against a house with me on top of it. Okay, so I'm clearly painting something. So here's my house. Okay, and a 4-meter ladder, which isn't that the same as 12 feet? Oh, geez. Okay, so here's the ladder. Okay, ladder, and I'm on top of it. Let's see. I have brown hair in a ponytail. Okay, and I like to smile, and I have blue eyes. Okay, so there. Eli runs into the ladder. Oh, this is 4 meters. Okay, 4 meters. Okay, so the ladder is sliding across. All right, so Eli runs into the ladder, and the ladder begins moving down the wall. Okay, so the ladder is moving down the wall. Okay, Eli ran into it. No surprise. The ladder is sliding across the ground. So the ladder is sliding across the ground too at a rate of 5 centimeters per second. So 5 centimeters per second. But I need meters. So 5 centimeters per second is the same as 0.05 meters per second. So I'm going to make this disappear so I don't mess myself up because I got to get my units right. Okay, so I'm moving across the ground at 0.05 meters per second. How fast am I falling? Okay, so this time we want to know how fast we're falling down because it's me, and that means the top of the ladder. How fast am I falling down when the ladder is 5 feet from the house? Ooh, the ladder, the bottom of the ladder is 5 feet from the house. So we need a snapshot of 5 feet here. Okay. So again, let's walk through this. All we know about triangles is Pythagorean theorem, which is a squared plus b squared equals c squared. But we're dealing with height, so I'm going to label the height of the ladder h, and the length is how far it is from the house. So that's my L. So this is really h squared plus L squared equals 4 squared because my hypotenuse is 4. Okay, we need to take the derivative of this because we're dealing with rates, and rate means derivative with respect to time. So we're going to take the derivative of all of this with respect to time, so d dt. So when we do that, we are going to get 2h dh dt plus 2l dl dt. That's that implicit differentiation. The derivative of 16, 4 squared, is 0. Now remember, we have several different variables. We have an h, we have a dh dt, we have an l, and we have a dl dt. So let's find what we've got. Do we have a height? Not yet. Do we have a dh dt? No, that's what we're looking for. Do we have an L? Ding, ding, ding. We have an L. It is 5. And we have a dl dt. So we need to go back and find this height. So I'm going to recreate my little dude here. And if I have a 4 and a 5 feet, oh man, who writes these problems? 5 feet in meters is what? 1.5. Okay, you know who writes these problems? Me. I have myself to blame. 1.5 meters. Okay, so we're going to use Pythagorean theorem to solve that, and we're going to say 1.5 squared plus b squared equals 4 squared, and then we're going to get our answer, and we get 3.7. So now we have an h. Okay, let's go fill these things in. So 2h is 3.7. dh dt, I don't know. I'm going to leave it. Plus 2L. My length, remember, is in meters, 1.5. dl dt is 0.05 equals 0. Now all we have to do from here is rearrange. So I'm going to multiply this all together. And let's see, I'm going to say 2 times 3.7, and I get 7.4. So I have 7.4 dh dt. I hope I'm not running off the screen. plus 2 times 1.5 times 0.05, and what do we get there? We get, I can't multiply, 0.15 equals 0. I'm going to do some rearranging, and I am going to get negative 0.15 divided by 7.4 is negative 0.2. So the dl dt is negative 0.02 meters per second. Okay, the only difference in this from the last problem was that this time we were looking for dh dt, and the first problem we were looking for dl dt. Does it really matter? No. So the moral of the story is you start with whatever formula you know. In the latter case, it's Pythagorean theorem. You take the derivative of the formula with respect to time. So you use implicit differentiation to do that. So you multiply everything by dh dt, dl dt. Plug in what you know, use whatever formula you need to figure it out. Make sure your units are the right ones. Like we had meters, feet, and centimeters in this. What a mess. Plug it all in, and you will find it. Okay, good job.